Hello everyone, my name is Mehdi Shokouhian. I'm an assistant professor from Morgan State University, and today I'm going to talk about recycled fiber reinforced concrete. In this presentation, I provide some introduction and background about the fiber reinforced concrete, and particularly recycled fiber reinforced concrete, some models for predicting the strength of these type of materials and at the member level, and finally some conclusions. Construction sector is one of the main contributors to the global warming, accounting for 36% of the total final energy use and 39% of the energy-related CO2 emission in 2018. Currently, world produces 16.3 billion cubic yard of concrete annually, and the number is expected to rise to over 20.4 billion tons by 2050. The manufacturer of the cement produces about 0.9 pounds of the CO2 for every pound of cement. 1 cubic yard of concrete is responsible for emitting about 400 pounds of CO2. Depending on the weather, exposure to road salt and subsoil preparation, concrete should last at least 15 years. But of course, that can go up to 30 years if the concrete is properly designed. Around 1 billion used tires disposed each year in the world. Only about 100 million tires are recycled. Since tire incinerating can lead to dangerous fire, spills, and air pollution, reusing tires as tire rubber particle and fibers can reduce the air pollution and the amount of the municipal solid waste releasing into the landfill. The sample weighted average carbon emission for recycling scrap tires are 124 kilogram CO2 equivalent per tons sold. A recycled tire, including rubber and fibers, can be introduced in concrete and asphalt mixture or as fill material in other pavement layers. In the 1950s, the concept of composite materials came into being, and fiber reinforced concrete was one of the topics of interest. Once the health risks associated with asbestos were discovered, there was a need to find a replacement for substance in concrete and other building materials. By the 1960s, steel, glass, and synthetic fibers were used in concrete. But research into new fiber reinforced concrete continues today. Fibers are usually used in concrete to control cracking due to the plastic shrinkage and to drying shrinkage. They also reduce the permeability of concrete and thus reduce bleeding of water. Some types of fibers produce greater impact, abrasion, and shatter resistance in concrete. And larger steel or synthetic fibers can replace rebar or steel completely in certain situations. Fiber reinforced concrete has all but completely replaced bar in underground construction industries such as tunnel segments, where almost all tunnel linings are fiber reinforced in lieu of using a rebar. Indeed, some fiber actually reduces the compressive strength of a concrete. But of course, there are more benefit in other the mechanical characteristics of the reinforced concrete materials. The amount of the fiber added to the concrete mix is expressed as percentage of the total volume of the composite, termed volume fraction, or VF, V sub F, typically ranges from 0.1 to 3%. The aspect ratio, L over D, or length over the diameter of the fibers, is calculated by dividing fiber length by its diameter. And fibers with a non-circular cross-section, use an equivalent diameter for the calculation of aspect ratio. If the fiber's modulus of elasticity is higher than the matrix or concrete or mortar binder, they help to carry the load by increasing the tensile strength of the material. Increasing the aspect ratio of a fiber usually segments the flexural strength and toughness of the matrix. Longer length results in better matrix inside the concrete, and finer diameter increases the count of the fibers. To ensure that each fiber strand is effective, it's recommended to use fibers longer than maximum size of the aggregate. Normal concrete contains 19 mm equivalent diameter aggregate. Fibers longer than 20 mm are more effective. However, fibers that are too long and not properly treated at time of the processing tend to ball in the mix and create workability problem. In this slide, you see different types of steel fibers. These are basically industrial steel fibers, like hooked end, twisted, and straight. Also, regarding the synthetic fibers, we have different type of synthetic fibers, different materials. From left to right, you see the polypropylene fibers, glass fibers, and carbon fibers. One of the main applications of a fiber reinforced concrete is pavement. As you know, we have two different types of pavement, flexible and rigid pavement. In flexible pavement, we usually use asphalt material, and rigid pavement, we use concrete material. The essential difference between the two types of pavement, flexible and rigid, is the manner in which they distribute the load over the subgrade. Rigid pavement, because of a concrete rigidity and stiffness, tends to distribute the load over a relatively wide area of subgrade. The concrete slab itself supplies a major portion of the rigid pavement's structural capacity. Flexible pavement, inherently built with weaker and less stiff material, does not spread load as well as concrete. Therefore, flexible pavement usually require more layers and greater thickness for optimally transmitting load to the subgrade. The major factor considered in the design of the rigid pavement is the structural strength of the concrete. For this reason, minor variations in subgrade strength have little influence upon the structural capacity of the pavement. The major factor considered in the design of the flexible pavement is the combined strength of layers. One further practical distinction between the concrete pavement and asphalt pavement is that the concrete pavement provides opportunity to reinforce, texture, color, and otherwise enhance a pavement. That is not possible with asphalt material. These opportunities allow concrete to be made exceedingly strong, long-lasting, safe, quiet, and architecturally beautiful. Concrete pavements on average outlast asphalt pavement by 10 to 15 years before needing rehabilitation. Developing cracks in concrete pavement is one of the major problems that can cause defects and failures. There are many different types of cracks in concrete pavement, including the plastic shrinkage concrete crack, that when the concrete is still in its plastic state before hardening, it is full of water. And when the water eventually leaves the slab, it leaves behind large voids between the solid particles. These empty spaces make the concrete weaker and more prone to the cracking. These types of cracking happens frequently, and it's referred to plastic shrinkage cracking. While plastic shrinkage cracks can happen anywhere in a slab or wall or any different type of concrete structure, they almost always happen at reentrant corners or with a circular object in the middle of a slab. So wherever that you have utilities or the pipes and drainage, so it's more prone to have a cracking there. Since the concrete cannot shrink around the corner, a stress will cause the concrete to crack from the point of that corner. The other types of the cracks are expansion concrete cracks. So just like a balloon, heat causes concrete to expand. When the concrete expands, it pushes against anything in its way. When neither has the ability to flex, the expanding force can be enough to cause concrete to crack. Expansion joints are used as a point of separation or isolation between other static surfaces, typically made of compressible materials like asphalt, rubber, or lumber. Expansion joints must act as shock absorbers to relieve the stress that expansion puts on concrete and prevent cracking. The other type of the cracks is heaving cracks. When the ground freezes, it can sometimes lift many inches before thawing and settling back down. This ground movement brought on by the freezing and thawing cycle is a huge factor contributing to concrete cracking. If the slab is not free to move with the ground, the slab will crack. The other type of the cracks is settling concrete crack. Ground settling below a concrete slab can cause cracking. And settling of that may be a result of a poor soil compaction underneath of the slab. And settling the cracks typically occurs in a situation where a void is created in the ground below the concrete surface. This is another reason. The other types of crack caused by overloading on the slab. This is very common and sometimes can be combined by other types of cracks mentioned earlier. And finally, the crack caused by premature drying. Now let's talk about the recycled steel fiber. In the recent years, several research studies have explored the potential of end-of-life tires by products in the construction industry. The reuse and rational disposal of ELT is a high priority goal of the tire business, since the increasing amount of this type of waste is serious environmental and public health threat. The reuse of waste tires has become the most sustainable strategy to enable the investment in ELT recycling. Approximately 15 to 25% by weight of a tire is composed of metal. So which is great. I mean, we basically can use this 15 to 25% in concrete as a recycled steel fiber. Recycled steel fiber are currently derived from the tire recycling industry using mechanical and thermal degradation processes such as tire shredding, cryogenic reduction, and pyrolysis. Use of a recycled steel fiber may reduce the emission of CO2 since recycling saves impressive amount of the energy, contributing to the reduction of the ecological footprint and promoting the environmental sustainability. The reinforcement of a cement-based material with discrete steel fiber is now a current practice for several applications such as industrial floors, tunnel lining, and prefabricated elements and hydraulic structures. Steel fiber reinforced concrete, or short SFRC, is increasingly adopted in prefabricated and in situ concrete structures, allowing the partial or total replacement of conventional reinforcement. The incorporation of industrial steel fibers, ISF, in reinforced concrete to improve the mechanical and durability performance of concrete structure has been investigated over the past 3 decades. The crack opening restraint provided by the reinforcement mechanism of ISF bridging the cracks leads to a significant increase of a post-cracking load bearing capacity and energy absorption performance. And these can result in increasing the strength and ductility as well as toughness. The stress redistribution provided by fiber reinforcement allows the ultimate load to be higher than the cracking load, notably significant for structures with high degree of support redundancy. Recent research demonstrates that RSF can be a viable alternative to commercially available ISF for use in steel fiber reinforced concrete without a significant decay in the relevant mechanical properties, provided that RSF present adequate geometric characteristics, which depends on a source, which is waste tire, and the recycling process. In this process, basically, the waste tires depends on, the type of the waste tires, the fibers or wires inside tires may have a different grade of steel, and depends on the manufacturer, they may have different mechanical characteristics. In addition to that, the recycling process may change the property of the fibers, especially in terms of aspect ratio. The results of experimental and numerical investigations aiming to characterize the tensile and bond behavior of RSF embedded in a cementitious matrix, as well as the compressive strength and flexural behavior of a notched recycled steel fiber reinforced concrete beams, show that recycled steel fiber may be suitable for the reinforcement of the cementitious composites with enhanced ductility and toughness property. In addition, the replacement of ISF by RSF in fiber reinforced concrete responds to the concept of the circular economy, as may impact on the reduction of energy consumption and greenhouse gas emissions. However, further research is needed to explore the possibility of using RSFRC applied in structural elements as an eco-friendly material to mitigate the challenges of the sustainable construction industry. Constitutive models describe the material responses to different mechanical conditions, which provides a stress-strain relations to formulate the governing equations. As we all know, steel is an isotropic material that provides identical strength in compression and tension, of course, at material level. When you look at the stress-strain relation of concrete material, typically the concrete is very strong in compression as compared to tension. According to ACI, modulus of rupture, which can be considered as a tensile strength, is considered as 7.5 lambda square root FC prime in US unit. Most of them, all of these empirical equations that are provided in standards, considering the tensile strength as a function of compressive strength, meaning that by increasing the compressive strength, you can expect that the tensile strength is also increased. But as I said, in concrete material, you cannot use concrete in tension without reinforcing that when you want to use as a structural member. So either with a steel bar or composite materials or even fibers, you need to reinforce the concrete wherever you have a tension. Either is a pure tension, which is very rare, or flexure that has a part of section taken to tension. Okay, so why understanding the material constitutive model is important? is because we want to use those information from the mechanical characteristic of a material in designing and analyzing a section. So if it's used as a structural member, and also in many cases, it's very costly if you want to do the experimental studies for different type of sections or different type of structural members. And instead, many of us know that numerical and computational modeling using finite element methods, such as programs such as ANSYS or Abacus, is very common. And with that, definitely we can get more accurate results if your models were verified with the physical test specimen result. So even for finite elements, using the finite element techniques, you need to implement an accurate constitutive model. So if you want to model a fiber reinforced concrete, of course, considering the fibers as a fiber in a concrete section, at research level, it's possible, but for generalizing that and use it as a design engineer is not very practical to model the fibers and do that all solid elements calculation and crack analysis. Of course, is not in most of the cases possible. That's why understanding the constitutive model and implementing that in our finite element software, it's important because we can model and predict the behavior of a fiber reinforced concrete as well as recycled fiber reinforced concrete. So for fiber reinforced concrete, there are lots of research that have been conducted on mechanical properties of the fiber reinforced concrete that we definitely can use those information in the modeling or simulating the structures. Of course, that is something that we can do for fiber reinforced concrete. But even for fiber reinforced concrete, due to the various type of the fibers and the different types of fiber in terms of the aspect ratio and also the size, diameter, and also the fiber content that you add to your concrete mix is very important. And so changing that fiber content can definitely change your material mechanical properties. So understanding that and characterizing these materials in terms of the mechanical characteristics, it's important because without that we cannot predict our structural behavior, okay, or a structural member behavior. When it comes to the recycled steel fiber reinforced concrete, it is even more complicated. The reason of that is because in recycled steel fiber reinforced concrete, the shape of the fibers are not identical. So we have different shapes and also different aspect ratio that we need to take into account when we want to consider these in using finite element methods or computational simulation to analyze our structure or structural member. One of the most recent research that has been conducted on constitutive model for SFRC is the research that was conducted by Young et al. In 2019, and they provided tensile strength, elastic modulus, Poisson ratio, and also the compressive strength of fiber reinforced concrete. So In this research, what they did was using a factor that is called RI, or reinforcement index. And the reinforcement index in their research is simply defined as multiplication of a volume fraction by aspect ratio. So that basically means the fiber content multiplied by aspect ratio, which aspect ratio is the length of the fibers divided by diameter of the fibers. Okay, so with that, with two parameters, one is RI, which is a reinforcement index, and the other is FCU, which is the compressive strength of the concrete that is used in making that fiber reinforced concrete material. This is a concept that can be also used in identifying the recycled steel fiber reinforced concrete mechanical properties and constitutive model. Their research was based on experimental and numerical results that they use in their work to come up with these constitutive model. Geometric characteristic of fibers is a main difference between recycled steel fibers and industrial steel fibers. A group of students from Oregon State University, from my research group, conducted a research on recycled steel fibers extracted from tires, and they visited a couple of recycling plants and tried to collect some of the wires and steel fibers extracted from the waste tire, and they brought those to the lab and randomly selected different batches from these different recycling plants, and then try to characterize the geometry of the fibers in terms of the length, diameter, and then determine aspect ratio, and also trying to see the frequency of these fibers within a batch. This is important because as I showed you in a previous slide, there is a relationship between the reinforcement index and the tensile strength, or compressive strength, elastic modulus, and so on. So by increasing the reinforcement index, you can increase the strength in tension, compression, and so on. So definitely enhancing the mechanical properties of the material. But how we can increase the reinforcement index? The reinforcement index is a multiplication of fiber contents or volume fraction by the aspect ratio. So definitely the aspect ratio has an impact on increasing or decreasing the strength of the the fiber reinforced concrete. So this will help us to identify that if you go with a weighted average, you can determine how much of these fibers with a certain aspect ratio or length and diameter are basically within that mix, and then try to see how that can affect the strength of the fiber reinforced concrete. And from there we can predict the behavior of a structural member or a structure at a larger scale. Okay, so as we discussed, the number of fibers added to a concrete mix is measured as a percentage of the total volume of the composite, termed as volume fraction, or VF. The VF is typically ranges from 0.1% to 3%. An aspect ratio L over D is calculated by dividing the fiber length by its diameter. And according to the previous study that I explained earlier, a typical aspect ratio ranges from about 30 to 150 for length of 6 mm to 75 mm. A previous research shows that fiber with a larger aspect ratio are more efficient at improving the flexural strength. Therefore, this can help us to incorporate the effect of different aspect ratio within the batch of the selected recycled fibers, and then see how this can impact on the strength of recycled steel reinforced concrete. Now let's talk about the computational modeling. An experimentally verified numerical model were used in this study to evaluate the performance of a flexural member made of fiber reinforced concrete, to conduct a parametric study to evaluate the performance of recycled steel fiber reinforced concrete. Athena was used in this research to conduct finite element analysis, a nonlinear crack analysis for concrete and fiber reinforced concrete for a flexural member. Athena belongs to a category of advanced analysis software such as Abacus or ANSYS, but it specifically focuses on reinforced concrete structures and brittle material. Athena is especially designed for concrete, and the main advantage is that even though the analysis described severe cracking, the program never fails finding a convergence solution. This is one of the problems that in many of these software, like even ANSYS, we really have a problem with the crack analysis, because the convergence of the model sometimes becomes very difficult. As mentioned, in this study, we conducted a verification with experimental results, and a very close agreement were achieved between the result of the finite element model and experimental results. I forgot to mention that this software, Athena, is capable to perform modeling of high temperature and fire loading on concrete structures. Also, modeling of structural durability and reinforcement corrosion, which is quite interesting. And now about our model. After we verified the model with experimental results, and we had the confidence to conduct a parametric study. We conducted a comprehensive parametric study on different factors, different parameters, which are considered as the main design parameters of a recycled steel fiber reinforced concrete. So these parameters include shape factors, fiber content, aspect ratio, and compressive strength of the concrete. When I talk about the compressive strength of concrete, of course, is the concrete itself, not fiber reinforced concrete. The shape factor that we consider is something that was not considered in a previous calculation of a reinforcement index, because as I told you, the reinforcement index was based on the multiplication of aspect ratio by the fiber content. But now we try to incorporate the shape factor into the equation. So the shape factor that we consider, because in industrial fibers is very easy to classify different shapes, try to see what is the effect of different shapes on the increasing the strength of concrete in compression, tension, or whatever. But in recycled steel fibers, the shape factors, of course, is very different. So we have different shapes, and some of them has some sort of like curvy shapes, and based on all of these different and various shape of the recycled fibers, which sometimes is quite random, we have to cover various shape factors within this study. So what we actually did was try to consider a range from 0.7 to 1.5 of shape factors. In some studies that were particularly focused on the shape factors. What they consider was for industrial fibers, they consider different factors for like a twisted fibers or hooked fibers or straight fibers, which was basically the reference, which is considered as a 1. So we try to incorporate the shape factors in the reinforcement index. And the other factor that we consider, as I said, is a volume fraction or fiber content. Based on the previous study that were recommended between 0.5 to 3%, we also consider that with a small intervals to try to define different scenarios that we can better evaluate the performance of these in different situations with different fibers, and combination of these variables to come up with different scenarios. The other thing was aspect ratio. The aspect ratio that we consider in this parametric study was between 55 to 500, with also some, small intervals to enhance the accuracy of the result. Regarding the compressive strength of the concrete, just a concrete concrete material, we consider 32 to 56 megapascal compressive strength, of course, in 28 days age. And this, after using these parameters, by multiplying the shape factors by fiber content and aspect ratio, we calculated a reinforcement index. And the reinforcement index within a range that we actually define, we came up with like a reinforcement index between 0.2 to 12, and try to see how this reinforcement index will influence on the strength of fiber reinforced concrete. The question now is how we incorporated the recycled steel fibers within this study. So considering that, based on the frequency of the aspect ratio that I initially told you, that how that's basically measured, and based on the the study that our researcher were done, how many different type of fibers within a random batch were considered, and how much is the aspect ratio of those, and how much is the frequency of that specific aspect ratio within the batch. And after that, we try to use a weighted average, and after that we should be able to determine the aspect ratio based on that weighted average. So as a result of that, we did lots of studies trying to see the correlation between different design parameters with tensile strength. And these plots are showing the different reinforcement index. The parametric study conducted in this research was based on the more than 500 different scenarios with all different parameters with the ranges that I mentioned previously. We try to see correlation between reinforcement index and the ratio between tensile strength of recycled steel fiber reinforced concrete with tensile strength of a concrete, just a regular concrete without fibers. And here you see the results. So these results were set for different shape factors from 0.7, 1, and 1.48. So as you see here, and this also shows that based on the different compressive strength of a concrete, how these results were changed to increase the ratio. And basically this is showing, where you have a 1, basically means these numbers or these cases, so it shows that the tensile strength has no significant increase, or yeah, just almost 1 basically means the tensile strength of recycled steel fiber concrete were equal to the tensile strength of concrete. That basically means no effect, or maybe very minor effect. But as you see, by increasing the reinforcement index, most of the cases depends on the shape factors or the compressive strength. You see a significant increase by increasing the reinforcement index on this ratio, which is ratio between the tensile strength of recycled steel fiber reinforced concrete over tensile strength of concrete. And after that, as a part of that result, which is still ongoing, these are showing some prediction models that were conducted based on the reinforcement index, FC prime, and the ratio between tensile strength of recycled steel fiber reinforced concrete over tensile strength of the concrete. And this model, which is based on the surface fitting, is what was extracted from this research. So meaning that by knowing the compressive strength of concrete and using the reinforcement index as defined, you can predict the tensile strength of recycled steel fiber reinforced concrete. So which could help us to design a member based on this tensile strength and see how much additional reinforcement is required. One thing that I need to mention here is that, because as I said, this research is still ongoing, is that RI, which is a reinforcement index, was defined here as a multiplication of a shape factor by volume fraction by aspect ratio. What we found from this research was that RI really need to be revised because the reinforcement index as defined is not really accurate. And of course, by just simply considering that as a multiplication of these 3 parameters, we cannot get the accurate result. So what we actually found was that the weight of each of these 3 parameters, like shape factor, fiber content, and aspect ratio, are different in increasing. So the focus of this study was on slabs, but first we tried to see how much increase we have in the tensile strength of a member made of recycled steel fiber reinforced concrete, and then try to implement that into a slab and try to see how much load bearing capacity of a slab can be increased. Another finding of this research was that the effect of the FC prime was not as significant as reinforcement index. As you see here, the effect of the reinforcement index on tensile, increasing the tensile strength, was very significant, but as compared to that, FC prime has a very, very small effect on increasing the FT or tensile strength of recycled and fiber reinforced concrete. Now let's talk about the conclusions. First of all, replacing the recycled steel fiber with industrial steel fiber to reinforce concrete structure has many environmental benefits and can reduce the amount of the CO2 emission, of course. Aspect ratio, fiber content, fiber shape factor, and concrete compressive strength are the main parameters in flexural and tensile strength of recycled steel fiber reinforced concrete members. Orientation, distribution, and density of fibers can significantly impact on a recycled steel fiber reinforced concrete mechanical characteristics. This was conducted by a few experimental studies that we did in our lab, and also many previous studies that were conducted before. Geometric characteristics of recycled steel fiber needs to be analyzed in order to predict the bending strength at the member level. Why? Because aspect ratio is one of the major parameter in changing the reinforcement index. And the reinforcement index that was previously introduced for fiber reinforced concrete need to be revised for recycled steel fiber reinforced concrete. So we incorporated the shape factor, but of course the weight of each need to be included in terms of how much effect each one has on increasing the load-bearing capacity of member or increasing the tensile strength of a member that's subjected to flexure or tension. Reinforcement index has a significant influence on flexural strength and can increase the tensile strength up to 2.9 times of the strength of a normal concrete without fibers. And the other thing is, recycled steel fiber reinforced concrete can be designed and utilized in concrete pavement to enhance the strength and durability. I would like to acknowledge the sponsor of this project, the Center for Integrated Asset Management for Multimodal Transportation Infrastructure Systems, in short CMTIS, from U.S. Department of Transportation, Region 3 University Transportation Center. Also, I would like to thank the organizer of International Conference Advances in Construction Materials and Structures for the opportunity, and thank our graduate students and Department of Civil Engineering, Morgan State University. Thank you, and I would be happy to answer your questions.